These are the answers to the AP Chemistry packet that covers Topic 3.1. On this slide, you can see Unit 3 at a glance. Unit 3 is entitled Properties of Substances and Mixtures. In this video, we will take a look at Topic 3.1, Intermolecular and Interparticle Forces. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 3.1, Intermolecular and Interparticle Forces. Here are some essential knowledge statements from the AP Chemistry course and exam description. London dispersion forces are the result of the Coulombic interactions between temporary fluctuating dipoles. London dispersion forces are often the strongest net intermolecular force between large molecules. Dispersion forces increase with increasing contact area between molecules and with increasing polarizability of the molecules. The polarizability of a molecule increases with an increasing number of electrons in the molecule and the size of the electron cloud. It is enhanced by the presence of pi bonding. The dipole moment of a polar molecule leads to additional interactions with other chemical species. Dipole-dipole interactions are present between polar molecules. The interaction strength depends on the magnitudes of the dipoles and their relative orientation. Interactions between polar molecules are typically greater than those between nonpolar molecules of comparable size, because these interactions act in addition to London dispersion forces. Ion-dipole forces of attraction are present between ions and polar molecules. These tend to be stronger than dipole-dipole forces. The relative strength and orientation dependence of dipole-dipole and ion-dipole forces can be understood qualitatively by considering the sign of the partial charges responsible for the molecular dipole moment and how these partial charges interact with an ion or with an adjacent dipole. Hydrogen bonding is a strong type of intermolecular interaction that exists when hydrogen atoms covalently bonded to the highly electronegative atoms, nitrogen, oxygen, and fluorine, are attracted to the negative end of a dipole formed by the electronegative atom, nitrogen, oxygen, and fluorine, in a different molecule or a different part of the same molecule. In large biomolecules, non-covalent interactions may occur between different molecules or between different regions of the same large biomolecule. Question 1. In chemistry, it is important to differentiate between an intramolecular attractive force and an intermolecular attractive force. In the diagram below, 4 water molecules are shown. Part A. Draw a circle around one example of an intramolecular attractive force. So the prefix intra means within. So within the molecule, that would be a covalent bond. Since we have 4 water molecules that are shown in this diagram, that means there are a total of 8 covalent bonds, and you could have drawn a circle around any one of them. So here's one example. That's another one. This one, that one, this one, that one, or any of these. So these are covalent bonds that are within the water molecule. Now, in part B, it says to draw an arrow that points to one example of an intermolecular attractive force. So now we're looking for those dotted lines that are in between the molecules of water. So that would be a possible answer, connecting 2 water molecules, or this one, or that one. Question 2. Consider an experiment in which a pure sample of H2O is heated to its boiling point. Part A. Circle the particulate diagram that best represents the gas particles that are formed above the surface of water in this experiment. Now, when water boils, we are just doing a change of phase from liquid to gas, but we are not breaking up the water molecules into individual atoms of hydrogen and oxygen. So that equation on the left side of the slide, that's not happening. Therefore, what is happening is that liquid water, H2O, is changing into water vapor, still H2O, so we should circle the particle diagram that shows molecules of water, and that is the particle diagram on the right. Part B, based on your choice in Part A, when a pure sample of H2O undergoes evaporation, what type of attractive forces are broken? Well, we're not breaking up the individual molecules and breaking covalent bonds. We are breaking the attractive forces in between the molecules. So intermolecular attractive forces are broken. Question 3. Each substance listed in the table above is classified as a covalent molecular substance. Based on the data in the table, which substance experiences the strongest intermolecular attractive forces in the liquid phase? Justify your answer by making a connection between the data in the table and what happens to the molecules in a molecular substance during evaporation. So of these three substances, methane, carbon tetrafluoride, and acetone, let's focus on the strongest intermolecular attractive forces being associated with the highest boiling point. So the correct answer is acetone. The data in the table shows that acetone has the highest boiling point, so acetone should experience the strongest intermolecular attractive forces in the liquid phase. So what does boiling point have to do with the strength of the intermolecular attractive forces? Well, the substance with the highest boiling point requires the most energy to break the attractive forces between the molecules. Now, you will note that this question did not ask you to discuss the polarity of the molecules, the London dispersion forces, the dipole-dipole forces, etc. Later on in the packet, questions 6 and 7 will ask you to revisit this data table and then give an explanation based on the specific types of intermolecular forces and the relative strength of the attractive forces between the molecules. But all we did in this particular question is say that the highest boiling point is associated with the strongest attractive forces between the molecules. London dispersion forces, named in honor of German-American physicist Fritz London, are a result of the Coulombic interactions between temporary fluctuating dipoles. So what does a temporary dipole look like? Consider the following example involving two atoms of neon. So there is no polarization of either atom, and the electron clouds are fairly evenly distributed. So something happens when these atoms move closer together. In the diagram above, the two atoms of neon were relatively far apart from each other, but when these atoms get closer together, the nucleus of one atom can become attracted to the electrons of the other atom and vice versa. In addition, repulsions can occur between the electrons of different atoms, and the electron clouds of each atom can become distorted, resulting in the formation of temporary dipoles as shown in the following diagram. So now we see two neon atoms with distorted electron clouds, and there is a partial negative charge and a partial positive charge with these distorted electron clouds. So the partial negative charge of one neon atom is attracted to the partial positive charge of another neon atom. Let me define a couple of terms here. Polarizability is the ease with which the electron cloud in an atom or molecule can become distorted. And London dispersion forces, or LDFs for short, are the attractions between atoms or molecules that are caused by temporary dipoles. I will put a link in the video description area to this video showing a flock of birds, a flock of starlings, and the murmuration of the starlings. So it's very beautiful to watch as this flock moves in various shapes and so forth. And I use this video as an analogy for how an electron cloud can become distorted. The larger the electron cloud, the greater the chances that that electron cloud can become distorted. That's called polarizability. Here are two molecules, CH4 and CCl₄, but one of them has a larger electron cloud. CH4 consists of one carbon atom, which is 6 electrons, and 4 hydrogen atoms, which are 1 electron each. So 6 plus 4 is 10. But CCl₄ would be a carbon atom, 6 electrons, plus 4 chlorine atoms that are 17 electrons each. So 4 times 17 is 68, plus 6 is 74. So CCl₄ has a much larger electron cloud, and you can see this in the model and compare. It turns out that CH4, which is methane, is a gas at room temperature, whereas CCl₄, carbon tetrachloride, is a liquid at room temperature. The boiling point of methane is 112 Kelvin, and the boiling point of carbon tetrachloride is 350 Kelvin. So there must be something about the size of the electron cloud that makes a difference in terms of the attractive forces between the molecules and the properties of each substance. The strength of the London dispersion forces increases as the number of electrons in an atom or molecule increases. The larger the electron cloud is, the more likely it is that the electron cloud can be distorted or polarized. In other words, the larger the electron cloud is, the more polarizable it is, and the stronger the London dispersion forces between the particles. Comparing the relative strength of the attractive forces between the particles helps us to make predictions about boiling points. The boiling point of a substance is related to the relative strength of the attractive forces between the particles. Question 4. Explain the trend in boiling point shown in each data table above in terms of London dispersion forces and the polarizability of atoms and molecules. So as we go from neon to xenon, we see an increase in the boiling point. Neon has 10 electrons, argon has 18 electrons, krypton has 36 electrons, and xenon has 54 electrons. So as you go from neon to argon to krypton to xenon, the size of the electron cloud increases and the boiling point also increases. The larger the electron cloud is, the more polarizable it is, and the stronger the London dispersion forces are between the particles. There is a similar trend in the other table as we look at the halogens from fluorine to chlorine to bromine to iodine. The boiling points increase. So the fluorine molecule has 18 electrons, whereas the chlorine molecule has 34 electrons, 70 electrons for the bromine molecule, and 106 electrons for the iodine molecule. So a similar trend as you go from fluorine to chlorine to bromine to iodine. The size of the electron cloud increases, and the boiling point also increases. The larger the electron cloud is, the more polarizable it is, and the stronger the London dispersion forces are between the particles. Let's take a look at question 5. We are given two different substances, pentane and 2,2-dimethylpropane. They have the exact same chemical formula, C5H12, but they have different structural formulas and how the atoms are connected to each other. Pentane has a boiling point of 309 Kelvin, whereas 2,2-dimethylpropane has a boiling point of 283 Kelvin. So there must be a reason to explain why pentane has a higher boiling point than 2,2-dimethylpropane. It's not about the size of the electron cloud because each substance has the formula C5H12. It must be about molecular shape, surface area, and contact area between molecules. Let's take a look. So pentane versus 2,2-dimethylpropane. If we compare these molecules, we can see that the pentane molecules have greater surface area and contact between the molecules, whereas 2,2-dimethylpropane has less surface area and contact between the molecules. So pentane is more spread out, whereas 2,2-dimethylpropane is more spherical. So the molecules of pentane have greater surface area than molecules of 2,2-dimethylpropane. This results in greater contact between molecules for pentane, and there are stronger attractions between molecules in pentane, resulting in a higher boiling point. Question 6. Review the information in the data table shown with question 3. Explain why CF4 has a higher boiling point than CH4. So as we can see in this data table, carbon tetrafluoride, CF4, has a boiling point of 145 kelvins, which is greater than the boiling point of methane, CH4. And the reason for this difference in boiling point is related to the relative size of the electron clouds for these two molecules. Now, carbon has a total of 6 electrons. Hydrogen has only 1 electron, but 6 plus 4 would give us 10 electrons for the CH4 molecule. Fluorine has 9 electrons, so 9 times 4 is 36, plus the 6 electrons for carbon. That gives the molecule CF4 a total of 42 electrons, so it has a larger electron cloud. And that difference in boiling points is related to the relative size of the electron cloud, and therefore the polarizability and the relative strength of the London dispersion forces between the molecules. So the answer to question 6 is the following. CF4, carbon tetrafluoride, has a larger electron cloud than CH4, methane. The larger the electron cloud is, the more polarizable the molecule is, and the stronger the London dispersion forces are between the molecules. More energy is required to break the attractions between the CF4 molecules, resulting in a higher boiling point. Now, unlike London dispersion forces, which are the result of temporary fluctuating dipoles, dipole-dipole forces are a result of the attractions between molecules that have permanent dipoles. The relative strength of dipole-dipole forces depends on the magnitudes of the dipoles and their relative orientation. So as a definition, dipole-dipole forces are the attractions between polar molecules in which the partial negative charge of one polar molecule is attracted to the partial positive charge on another nearby polar molecule. For example, HCl is a polar molecule, and since chlorine is more electronegative than hydrogen, there is a partial positive charge on the hydrogen atom and a partial negative charge on the chlorine atom. So when two HCl molecules are near each other, they experience dipole-dipole forces in which the partial negative charge of one molecule is attracted to the partial positive charge on another molecule. If we compare two different molecules that have comparable size electron clouds, the attractions between polar molecules tends to be greater than the attraction between non-polar molecules. And this can be explained because the dipole-dipole attractive forces act in addition to the London dispersion forces. As an example, here are two molecules with comparable size electron clouds. Nitrogen, N2, has 14 electrons. Carbon monoxide, CO, also has 14 electrons. But the boiling point of CO is slightly greater than the boiling point of N2. And that's because N2 is nonpolar and only experiences London dispersion forces, whereas CO is polar and experiences both London dispersion forces and dipole-dipole forces. Question 7. Review the information in the data table shown with question 3. Explain why acetone has a higher boiling point than CF4. So earlier in the video with question 6, it had to do with the difference in the size of the electron cloud between CF4 and CH4. It was about the strength of the London dispersion forces. But now we're comparing CF4, carbon tetrafluoride, and C3H6O, acetone. These two molecules actually have pretty comparable, similar size electron clouds. So it's not about the size of the electron cloud, it's about the polarity. CF4 is classified as a nonpolar molecule, so it has tetrahedral geometry and all the bond dipoles cancel out, whereas acetone, which has a central atom with trigonoplanar geometry, the dipoles in that molecule do not cancel each other out. And since acetone is polar, it will experience both London dispersion forces and dipole-dipole forces. So CF4 is a nonpolar substance that experiences only London dispersion forces, or LDFs for short, between its molecules. On the other hand, acetone is a polar substance that experiences both LDFs and dipole-dipole forces. And since acetone experiences stronger intermolecular forces, then more energy is required to break the attraction between the molecules, resulting in a higher boiling point. Question 8 is similar to question 7, but the difference is that instead of being given the boiling point of each substance and having to explain why, you have to make a prediction about which substance should have a higher boiling point and then justify your answer. You have to justify your answer in terms of the polarity of the molecules, the type of intermolecular forces experienced by each substance, and the relative strength of the intermolecular forces. So we have ethane, C2H6, and we have fluoromethane, CH3F. Here are the structural formulas of each molecule: ethane, C2H6, and fluoromethane, CH3F. So since ethane is very symmetrical and all of the bond dipoles cancel out, ethane is nonpolar, whereas CH3F, because of its asymmetry, the bond dipoles do not cancel out. That is a polar molecule. So what type of intermolecular forces are experienced by each substance? Ethane can only experience London dispersion forces, or LDFs, whereas fluoromethane can experience both LDFs and dipole-dipole forces because it is polar. So therefore, the relative strength of the intermolecular forces should be greater for fluoromethane. So ethane is a nonpolar substance that experiences only London dispersion forces, or LDFs, between its molecules. Fluoromethane is a polar substance that experiences both LDFs and dipole-dipole forces between its molecules. Since fluoromethane experiences stronger intermolecular forces, more energy is required to break the attractions between the molecules, resulting in a higher boiling point. In question 9, we are told that a mixture of CCl₄ gas and HCl gas is at a temperature of 600 kelvins. This mixture is cooled to 340 kelvins, and at this temperature, the CCl₄ condenses, changing from a gas into a liquid, while the HCl remains in the gaseous state. Answer the following questions based on this observation. Part A. Identify all types of intermolecular forces present in each substance. CCl₄ is classified as a nonpolar molecule, so therefore it only experiences London dispersion forces. HCl is classified as a polar molecule, so it will experience both London dispersion forces and dipole-dipole forces. Part B. Which substance, CCl₄ or HCl, has the higher boiling point? Now, what makes this question challenging is that the information you are given seems to contradict the predictions that you might have made on your own regarding which substance should have stronger intermolecular forces. So if you are given experimental data, pay attention to the data. Before I answer part B, which substance has the higher boiling point, let's take a look at the following scenario. Suppose you have two different substances that are liquids at room temperature, and they are labeled as A and B. Pure samples of each substance are placed into separate beakers, and the beakers are heated gently. At a temperature of 310 Kelvin, substance A reaches its boiling point. Substance B has not yet reached its boiling point. So, substance A has a lower boiling point. Substance B has a higher boiling point. I'll just make up some numbers. So 310 Kelvin is the boiling point of substance A, and suppose that 350 Kelvin is the boiling point of substance B. Now, let's continue thinking about these two substances in the following situation. We have a container with both A and B, and the temperature inside the container is 400 Kelvin. The boiling point of substance A is 310 Kelvin, and the boiling point of substance B is 350 Kelvin. So with this mixture at 400 Kelvin, both substances are in the gas phase. This can be explained because the temperature inside the container, 400 Kelvin, is greater than the boiling point of both substances. Now think about what will happen inside this container when the temperature is decreased to 340 Kelvin. One of them is going to condense into a liquid. So now take a look. We are at 340 Kelvin. At a temperature of 340 Kelvin, some of the particles of substance B have condensed into droplets of liquid because 340 Kelvin is lower than the boiling point of substance B, which was 350. At a temperature of 340 Kelvin, substance A is still in the form of gaseous particles because 340 Kelvin is higher than the boiling point of substance A, which was 310. So let's go back and analyze the situation. If liquid B has a higher boiling point than liquid A, which substance experiences stronger intermolecular attractive forces? Well, the one that has the higher boiling point, so liquid B. If, under a situation at a certain temperature, one of them condenses into a liquid, whereas the other remains as a gas, which substance experiences stronger intermolecular attractive forces? The one that has condensed into a liquid. So now back to part B. Which substance, CCl₄, or HCl, has a higher boiling point? Let's take a look at the data. CCl₄ condenses, changing from a gas to a liquid, while the HCl remains in the gaseous state. So the answer to part B is that CCl₄ has the higher boiling point. This can be explained because at this temperature, 340 Kelvin, CCl₄ condenses and is able to exist in the liquid phase, whereas HCl exists in the gas phase. So whatever the boiling point of HCl is, it's already reached that value. So CCl₄ can exist as a liquid, whereas HCl has already passed from a liquid to a gas at this temperature. On to part C, very similar situation. Which substance experiences stronger intermolecular attractive forces? The answer is CCl₄, and that's because at this temperature, the particles of CCl₄ have come together, condensing to form droplets of liquid, whereas the HCl is still in the form of a gas. So liquid, stronger intermolecular attractive forces. Question 10. The table above gives the molecular structures and boiling points for the compounds CS₂, carbon disulfide, and COS, carbonyl sulfide. Answer the following questions based on the information in the data table. Part A. Identify all types of intermolecular forces present in each substance. So because of symmetry, carbon disulfide is a non-polar molecule in which the bond dipoles cancel each other out. So since CS2 is nonpolar, it can only experience London dispersion forces. We don't have that same symmetry with the carbonyl sulfide compound. We have a sulfur on one side and an oxygen on the other. Since the dipoles in that molecule do not cancel out, it is a polar molecule. So it will experience both London dispersion forces and dipole-dipole forces. Part B, which substance, CS2 or COS, experiences stronger intermolecular attractive forces? Remember, if you are given a data table, you have to go with the data that you're given. So since CS2 has a higher boiling point than COS, it must experience stronger intermolecular attractive forces. That might not be what you would have predicted, but you are given the data, so you have to go with the data. So CS2 has the higher boiling point. Questions like number 9 and number 10 can be challenging for AP Chemistry students, so here are some helpful guidelines. It is important to pay attention to the data you are given. This is especially true when the data seems to contradict the predictions that you might have made on your own based on the molecular structure, polarity, and the types of intermolecular forces present in each substance. It is possible that a nonpolar molecule with a large electron cloud can have a higher boiling point than a polar molecule with a small electron cloud. For example, octane, C8H18, is a nonpolar molecule, and that substance boils at 125 degrees Celsius, whereas water, H2O, is a polar substance that boils at only 100 degrees Celsius. Now suppose you compare two different molecules that are both nonpolar. Suppose that one molecule has a larger electron cloud than the other molecule. The molecule with the larger electron cloud should be more polarizable, experience stronger London dispersion forces, and have a higher boiling point, which we have seen earlier with CH4 and CF4, both nonpolar, but CF4 had the larger electron cloud. Suppose you compare two different molecules whose electron clouds are approximately the same size. Suppose that one molecule is nonpolar and the other molecule is polar. The polar molecule should experience stronger intermolecular attractive forces, that is, a combination of LDFs and dipole-dipole forces. So the polar substance should have a higher boiling point, and we saw that earlier with CF4 and C3H6O, that the polar molecule on the right had stronger attractive forces between the molecules and a higher boiling point. Now, suppose you compare two different substances and one of them is a nonpolar molecule with a larger electron cloud and the other is a polar molecule with a smaller electron cloud. In this situation, you cannot make a prediction about which substance will have stronger intermolecular attractive forces. However, if you are given a table of experimental data, pay attention to the data. So we wouldn't have predicted that CS2, the nonpolar molecule, actually had a higher boiling point than COS, but if you're given data, then you have to go with the data. In question 11, it says, identify all of the intermolecular forces present between molecules in each substance in the table above. So we have Br2 and BrCl. Explain the difference in boiling points by comparing the relative strength of the attractive forces between molecules. So Br2 is a diatomic molecule in which the atoms are the same, so it's going to be classified as a nonpolar molecule and can only experience London dispersion forces. BrCl is also a diatomic molecule, but the atoms are different, so that molecule is classified as polar. It can experience both London dispersion forces and dipole-dipole forces between the molecules. We have to come up with a reason why Br2, the nonpolar molecule, actually has stronger attractive forces between the molecules because Br2 has the higher boiling point. So it must have something to do with the size of the electron cloud. Chlorine has 17 electrons. bromine has 35 electrons. So the Br2 molecule has a larger electron cloud and greater polarizability than BrCl. The London dispersion forces in liquid Br2 must be stronger than the combined intermolecular forces, the combination of LDFs and dipole-dipole forces in the molecule BrCl. So thus the boiling point of Br2 is greater than that of BrCl. We're going to go with the data and then make an argument about the size of the electron cloud and the greater polarizability of the Br2 molecules. All right, let's move on to question 12. Explain the trend in boiling point shown in the data table above in terms of London dispersion forces and the polarizability of the molecules. So each substance in this table, CH4, SiH4, GeH4, and SnH4, are classified as non-polar substances because they have tetrahedral geometry, very symmetrical. So what we're looking at here is as we go from carbon to silicon to germanium to tin, the number of electrons in the electron cloud is increasing. And we've seen this trend before with the noble gases and with the halogens. So as the size of the electron cloud increases, the boiling point also increases. The larger the electron cloud is, the more polarizable it is, and the stronger the London dispersion forces are between the particles. As we transition from question 12 to question 13, we have to pay close attention to certain molecules that are going to break the trend or the pattern. So London dispersion forces tend to increase with the size of the electron cloud and the polarizability of the molecules. So in each of the sets shown above, there is a trend in which a larger electron cloud results in more polarizability and a higher boiling point. NH3, PH3, ASH3, and SBH3, size of the electron cloud is increasing in set 1, and then in set 2, the same pattern, H2O, H2S, H2SE, H2TE, size of the electron cloud is increasing. And then in set 3, HF, HCl, HBr, HI, size of the electron cloud is increasing. But we're looking for a certain exception to the trend, molecules that break the trend. Question 13, circle 3 substances shown in the tables above that have the following properties. The molecule has a relatively small electron cloud, and the substance has a relatively high boiling point compared to the other substances in the same set. Now, in set 1, the boiling points generally increase from pH3 to ASH3 to SBH3, but NH3 seems to defy this trend because although it has the smallest electron cloud in that set, it has a rather high boiling point. In set 2, H2O is the smallest electron cloud in that set, and yet it has the highest boiling point. In set 3, HF has the smallest electron cloud in that particular set, and yet it has the highest boiling point. So what's going on here is something called hydrogen bonding, which is a special kind of attraction. Let's take a look at the details of hydrogen bonding. You'll notice that in terms of electronegativity, nitrogen, oxygen, and fluorine have rather high values for electronegativity. So that's part of what's going on with hydrogen bonding. Hydrogen bonding is an important type of attractive force that involves the following details. One substance behaves as a hydrogen bond donor. The other substance behaves as a hydrogen bond acceptor. So what are the requirements for a substance to be a hydrogen bond donor? Well, the substance must contain a hydrogen atom that is bonded, covalently bonded to a highly electronegative atom, and the atoms are nitrogen, oxygen, or fluorine. What are the requirements for a substance to be a hydrogen bond acceptor? Well, the substance contains this highly electronegative atom, so either nitrogen, oxygen, or fluorine, with a lone pair of electrons on it. And this atom has a partial negative charge on it because it's part of a polar bond or a dipole. Let's take a look at two molecules of NH3. Here is an example of a hydrogen bonding interaction between two molecules of NH3. The one molecule behaves as a hydrogen bond donor because hydrogen is directly bonded to nitrogen, and the other molecule behaves as a hydrogen bond acceptor because it contains nitrogen in a polar bond with a lone pair of electrons on it. Here are two molecules of water with a hydrogen bond between them, and that hydrogen bond interaction involves a hydrogen bond donor, so there's a hydrogen directly bonded to oxygen, and on another molecule there is an oxygen with a lone pair that's part of a polar bond. And then with two molecules of HF, one molecule serves as a hydrogen bond donor, H directly bonded to F. The other molecule behaves as a hydrogen bond acceptor, with the fluorine and the lone pair of electrons part of a polar bond. All right, let's take a look at question 14. Both HF and CH3F contain one fluorine atom and at least one hydrogen atom. Part A, draw a diagram to show how an HF molecule can form a hydrogen bonding attractive force with another HF molecule. So there's the donor and the acceptor that we were just talking about. But in part B, it says explain why CH3F cannot form a hydrogen bonding attractive force with another CH3F molecule. So what's the problem with CH3F? Well, in order to be a hydrogen bond donor, the hydrogen atom in the substance must be directly bonded to either N, O, or F. And you can see that in this molecule, the hydrogen atoms are bonded to carbon, not fluorine. So the reason why in part B, CH3F cannot form a hydrogen bonding attractive force with another CH3F molecule is because it cannot serve as a hydrogen bond donor. The hydrogen atoms in the molecule are bonded to carbon. They are not bonded directly to a fluorine atom. Question 15. Use the information in the data table above to draw the correct Lewis electron dot diagram for compound 1 and compound 2 in the boxes below. Include all bonding pairs and non-bonding pairs. Each atom in each diagram should have a formal charge of 0. Now, what's interesting about this question is that we have the exact same molecular formula, C2H6O, but the molecule on the left, compound 1, cannot form hydrogen bonds with itself, and the molecule on the right, compound 2, is able to form hydrogen bonds with itself. Remember that for hydrogen bonding to occur, to be a hydrogen bond donor, the hydrogen should be directly bonded to either nitrogen, oxygen, or fluorine. So I'm going to prevent that from happening in compound 1, and then I'm going to enable that to occur in compound 2. So here's my skeleton for compound 1. The connectivity of the atoms could be C bonded to O, bonded to C, but the oxygen atom is not bonded directly to hydrogen. And then for compound 2, I do want the oxygen to be directly bonded to hydrogen, so C bonded to O, bonded to H. Let me go ahead and complete the skeleton structure. I need 6 hydrogens. So there is C2H6O on the left, but that molecule, compound 1, cannot form hydrogen bonds. And then on the right, C2H6O, that molecule can form hydrogen bonds with itself. Remember to include all of the non-bonding pairs of electrons, which means I need 2 lone pairs of electrons on the oxygen in each of these Lewis electron dot diagrams. Each atom in each diagram does have a formal charge of 0. So compound 1, which is known as dimethyl ether, is a gas at room temperature. It has a boiling point of 249 Kelvin, and it is not able to form hydrogen bonds with itself. Compound 2, which is known as ethanol, is a liquid at room temperature. It has a boiling point of 351 Kelvin, and it is capable of forming hydrogen bonds with itself. All right, questions 16 through 18 are good examples of whether things can or cannot serve as hydrogen bond donors or acceptors. Let's take a look. Number 16. Explain why NH4+, which is the ammonium ion, can behave as a hydrogen bond donor, but it cannot behave as a hydrogen bond acceptor. Well, the reason why it can behave as a hydrogen bond donor is because there is a hydrogen atom bonded directly to a nitrogen atom. So that does fulfill the requirement to be a hydrogen bond donor. However, the reason why it cannot serve as a hydrogen bond acceptor is that the central atom, the nitrogen atom, does not have a lone pair of electrons on it. Question 17. Explain why NCl₄ can behave as a hydrogen bond acceptor, but it cannot behave as a hydrogen bond donor. The reason why NCl₄ can behave as a hydrogen bond acceptor is that it does contain a nitrogen atom with a lone pair of electrons that's part of a polar bond, but it cannot behave as a hydrogen bond donor because the molecule does not contain a hydrogen atom at all. Question 18. Explain why NH2Cl can behave as both a hydrogen bond donor and a hydrogen bond acceptor. So it can behave as a donor because there is a hydrogen atom directly bonded to a nitrogen atom, and it can behave as an acceptor because the nitrogen atom contains a lone pair of electrons and is part of a polar bond. Question 19. Explain why the diagram on the left does not represent a hydrogen bonding attractive force. If you look carefully, you'll see that there is a hydrogen directly bonded to carbon, and so that's the problem. If a molecule is going to behave as a hydrogen bond donor, then the hydrogen must be directly bonded to either nitrogen, oxygen, or fluorine. So that's the problem. That particular hydrogen atom is bonded to carbon. It is not directly bonded to oxygen. So in the box on the right, draw a hydrogen bonding attractive force as a dashed line. So I have to use one of the hydrogens that is directly bonded to oxygen and then have that connection be to the oxygen on the other molecule. So you could have drawn the dashed line like this, where that hydrogen on the top molecule is directly bonded to oxygen and it reaches out to form a connection with the other molecule, and that would be the oxygen. Or you could have drawn your dashed line like this, where the hydrogen in the bottom molecule is directly bonded to oxygen, and it reaches out to form a connection with the oxygen on a nearby molecule. So either this or this would have been acceptable as your choices there. In a large molecule, it is possible for a hydrogen bonding attractive force to be formed between a hydrogen atom bonded to N, O, or F, and the negative end of a dipole formed by N, O, or F in another region of the same molecule. Examples of this situation can occur in large biomolecules such as proteins, carbohydrates, and DNA. Question 20. Thymine and adenine form a base pair in the DNA molecule. In the diagram below, thymine is shown at the left and adenine is shown at the right. The bases are attached to the backbone portion of the DNA strands. Draw two dashed lines to represent two hydrogen bonding attractions on the diagram below. So before I show the correct hydrogen bonding attractions, I'm going to get rid of any hydrogens that are directly bonded to carbon and eliminate them as possibilities. So it could not be this hydrogen or these three hydrogens or this one down there. Those hydrogens are directly bonded to carbon, so they wouldn't count. Now, this hydrogen is directly bonded to nitrogen, and so is that one. So I could form a connection between the hydrogen and then either an oxygen or a nitrogen. So my two hydrogen bonding attractions would look something like this. There's the dashed lines to represent two different hydrogen bonding attractions. And so as you can see on this slide, we have examples of base pairs in DNA. So the G and the C, that represents guanine and cytosine, and the A and the T represents adenine and thymine. So hydrogen bonding attractions between base pairs are represented by the dashed lines in this diagram. Ion-dipole forces represent an attractive force between an ion and a polar molecule. They usually occur in a solution when an ionic compound is dissolved in a polar solvent, such as water. Coulomb's law can be applied when comparing the relative strength of an ion-dipole attractive force. The attractive force between an ion and a polar molecule should increase as the magnitude of charge on the ion increases and as the size of the ion decreases. So here is Coulomb's law, which has a numerator. Q1 and Q2 has to do with the magnitude of the charge, and then r squared in the denominator that has to do with the distance between the particles. The greater the charge magnitude, the stronger the attraction between the oppositely charged particles. We're talking about a water molecule and one of these four ions. Which ion in the table above is most likely to have the strongest interactions with nearby water molecules? If I have to choose between -1 and -2, I would choose -2 because that is a greater charge magnitude. Now, as far as the distance, if they are closer to each other, the smaller the distance between the charged particles, the stronger the attraction should be. So I'm going to pick the smaller ionic radius because that will make it closer to the water molecule. So the correct answer here is the sulfide ion, S2-, should have the strongest interaction with a nearby water molecule because it has a higher charge magnitude and has a smaller ionic radius. Question 22. A small amount of solid sodium chloride is dissolved completely into water to form a solution of aqueous sodium chloride. Draw a particle diagram below to represent the attractions between the ions and the surrounding water molecules. In your drawing, each ion should be surrounded by 3 water molecules with the proper orientation based on the charge of the ion and the direction of the dipole in the water molecule. Use the following symbols in your diagram. So we have sodium, Na+, we have chloride, Cl-, and then we have a water molecule. And in the water molecule, which is polar, the oxygen end of the water molecule is going to have a partial negative charge, and the hydrogen end of the water molecule has a partial positive charge. That's because oxygen is more electronegative than hydrogen. So if I have a sodium ion, which is positively charged, I want the negative end of the water molecule, which is the oxygen, to be pointed toward the sodium ion. So opposite charges attract. So the negative end of the water molecule would be the oxygen. And then I would flip it around. If I have a chloride ion, which is negatively charged, then I want the positive end of the water molecule, which would be the hydrogen end, to be pointed toward the negative ion. Again, opposite charges attract. If you're wondering if you have seen something like this before earlier in the study of chemistry, back in topic 4.2, which was net ionic equations, I did present a question like this. We're talking about how you represent electrolytes and so forth. So you may have seen this before. That should look familiar to you. Again, ion-dipole forces, attraction between ions and polar molecules. So in preparation to answer question 23, let's take a look at the information in this data table. Ethane, formaldehyde, and methanol are given with their structural formulas. We also have boiling points. Let's fill in the missing information in the data table. For molar mass, we can use the periodic table to figure out that value. So for ethane, that would be 2 carbons and 6 hydrogens. So if we add up the atomic masses, we get approximately 30 grams per mole. For formaldehyde, it would be 1 carbon, 1 oxygen, and 2 hydrogens. If we do that math, Adding up the atomic masses from the periodic table, we also get approximately 30 grams per mole. And then for methanol, 1 carbon, 1 oxygen, 4 hydrogens, we get approximately 32 grams per mole. Each of these substances has a comparable size electron cloud. They're all pretty similar to each other. Now, with respect to polarity, ethane is a very symmetrical molecule in which all the dipoles would cancel out, so ethane is classified as nonpolar. Formaldehyde has trigonal planar geometry, but the dipoles do not cancel out. We have hydrogen, hydrogen, oxygen, so that is a polar molecule. And then methanol is also a polar molecule in which the dipoles do not cancel each other out. Now, in number 23, part A, we have to identify all types of intermolecular forces present in each substance. Since ethane is nonpolar, it would only experience London dispersion forces. Since formaldehyde is polar, it would experience both London dispersion forces and dipole-dipole forces. And you'll notice in methanol, there is a hydrogen directly bonded to an oxygen, so it's capable of experiencing hydrogen bonding interactions. It's also polar, so it experiences all three: London dispersion forces, dipole-dipole forces, and hydrogen bonding. In part B, it says explain the differences in boiling point shown in the data table above in terms of the relative strength of the intermolecular forces. You can see that formaldehyde has a higher boiling point than ethane. So formaldehyde experiences stronger intermolecular forces than ethane. More energy is required to break the attractions between molecules, resulting in a higher boiling point. And you can see that methanol has a higher boiling point than formaldehyde. So methanol experiences stronger intermolecular forces than formaldehyde. More energy is required to break the attractions between molecules, resulting in a higher boiling point. All right, well, that particular question, number 23, that's the last question in the packet. This is the end of the video for topic 3.1. I hope that you found those answers and explanations helpful. Thanks for watching.